Okay, I think we can have a quick resolution to the problem of, believe it or not, to the general rotation of R3 and flipping through a plane or reflecting through a plane in R3. Now, we already established previous video, we have the formula for a matrix that will revolve R3 about the x-axis, the y-axis, and the z-axis. Now, what do we mean by a general rotation? Well, here's the idea, or here's what we're after. Okay, here's our x, y, z coordinate system, and the idea of a general rotation is general rotation of R3 is the following. We have a line. Now, the line has to go through the origin, and we revolve R3 about that line. The x and the y, z axis, fine, they're lines, but they're just three specific ones. Why does it have to go through the origin? Remember, for linear transformations, the origin has to map to the origin. So that's why we have to maintain that restriction. Now, how do we specify a line in R3? Well, there's several ways to do it, but the easiest way is just to have a direction vector. And normally we would have all multiples of a direction vector plus an additional vector, which situates that line in three-dimensional space. But since it goes to the origin, that's the zero vector. So how should I draw this here? Here's our direction vector. Now this is just generally coming out in space. I'm thinking of it as coming out towards us, but really it could go in any of the 8 octants of R3. Here's the idea. It's going to be, I think, a remarkably simple idea. Is we want to rotate R3. So imagine the vector's coming out, this way. We want to rotate R3 about the z-axis. Oh, before I say this, you could do this, and there's other ways you could do this, but I have to pick a way. So rotate about R3 so that this vector winds up in the xz plane. We can do that because we have a matrix to do that. If you tell me the angle we have to rotate through, we've got it. Once we're there, rotate about the y-axis so that this vector, which was now in the xz plane, is now coincident with the x-axis. How can we rotate about the y-axis? We've got a matrix to do that. Previous video, got the formulas all set. Then, once we're there, we'll rotate about the x-axis to the desired number of radians that we would have specified up front. Oh yeah, so up front we'd say we have a line and we want to rotate it through, I don't know what, theta radians. So what we do is we take this vector, rotate about the z-axis to put it in the xz plane, rotate it about the y-axis to put it coincident with the x-axis, rotate it about the x-axis, the required number of radians, and then, you guessed it, reverse the process. And that will achieve the rotation. So the only thing we have to say, remember, we would be given, I don't know what letters I want to use, maybe theta originally. We would be given that we want to rotate R3 theta radians about this direction vector v. So we're given this direction vector v. The only thing that we have to determine is how many radians we have to rotate through about the z-axis, and then how many radians about the y-axis. And if I was being a little slicker about this, we would just immediately refer to formulas for polar coordinates. We could look this up, or we could go back to our Calc 3 textbook. But let's just see if we can figure this out. Now, this direction vector right here, I'm not sure until I do this is going to make much of a difference. We could assume the magnitude is 1. Well, that may or may not make any difference here. But let's say v is the vector. Let's say x sub naught, y sub naught, z sub naught. Hopefully that comes out on the screen. So there's our vector. How How do we know how many degrees to rotate about z? Well, this is the old, I'm sure you've seen this before, right? But you project this down, onto the xy plane like this. And we're after this angle here. Let's call it alpha. So how do we get alpha? Well, let's see. What do we have here? This is the y coordinate. That's y sub naught. And this is x sub naught. And how do we get that angle there? Let's see. There's our, got to make sure I draw the right triangle in the right spot. There's our right triangle. So what are we looking at? Tangent. So tangent of alpha is equal to y sub naught over x sub naught. And so alpha is equal to tangent inverse of y sub naught, x sub naught. That's the angle that we'll use to rotate R3 about z. So go back and look at the formula. When you look at the formula for rotation about the z-axis, you only need to know the angle. Which angle? It's this angle here. Okay, what's the other angle? Let's see. What's the other angle we're going to need? Well, then we would have rotated. Well, let's see. We would have rotated this vector, and now it would be looking something like this. I'm attempting to put this vector here. This vector here. I've slammed it in the xz plane. And now I need to figure out let's see. Well, what this angle is right here, beta. Oh, there's one of the details just popped into my head. I hope I won't forget. I'll mention in a minute. Well, here, I'll mention it right now. When we did those matrices and we had the angle to rotate about an axis, I had to be careful, or I had to make some arbitrary decisions on how to rotate. So, for example, let's see. In this first rotation of alpha, is this the way I rotated things? Actually, if you think about it, no, the rotation was, to give a right-handed coordinate system, was x to y. So we have z preserved this way. So actually, we need to rotate about not alpha, but negative alpha. So I need to put a negative sign there. Hopefully that comes out. I don't know why I bothered making that blue here. Let's see, here we go. So there's alpha. Otherwise, I would actually rotate the vector this direction, and I don't know where it would wind up. Okay, so how do we find beta? Let's see. Let's see, how should we find beta? Actually, how should we find beta? This is where it's really tempting just to use the formulas from Calc 3. But let's see if we can pick this off somehow. What do we know? We know the magnitude here. And, we just need to find, that's the same. This is the same angle as right here, going from here to here. Beta appears here in this picture, where this is the projection of the vector down to the xy plane. So how do we get this angle right here? Hey, without loss of generality, we could just say that v is a unit vector. Hey, if it's not a unit vector, right, you could take the vector and divide by the magnitude of that vector and turn it into a unit vector. It would still give you the same direction vector. It would give you the same line. So again, there's no loss of generality. Why am I bothering to mess around with that? Well, now after I said all that, I don't have to bother with that. This height right here, what is that? That's z sub naught. And we know this length along here. Well, it is 10. What would that length be? Use Pythagorean theorem. That's x sub naught squared plus y sub naught squared. You take the square root of all that. Okay, fine. We'll do it that way. So what do we have here? We have tangent of beta. Tangent of beta is opposite. So that's z sub naught over the square root of x sub naught squared plus y sub naught squared. Hey, notice what I could have done here. I mean, like I said, I could have assumed that magnitude is 1. And so instead of using tangent, we just as well could have used sine. So sine in this angle would be z over this. Oh, that's so much nicer. You know what? Let's do that. It'll just be so much nicer looking than that horrible expression there. So sine of beta is, notice how nice it is if I choose that to be a unit vector. It'll be z sub naught over 1. So that's just z sub naught. So beta is equal to sine inverse of z sub naught. Hey, one comment, you may say, wait a minute, what if z sub naught is greater than 1? Well, it couldn't be greater than 1 because in the magnitude of this vector, it would be greater than 1. Okay, so there's beta, there's alpha. Hey, notice if you Google this sort of thing, and you find different websites, or I don't know, whatever the information you find, you may see some formulas that involve sines, some that say tangent. I mean, you're going to get the same answer. So you make the call, but I think that looks easier. It's almost tempting for me to want to go back and see maybe we could get an easier expression for this, but I don't mind this too much. This doesn't look too bad at all right here. So that's beta. Oh, hey, I have to make sure that we're using the matrices right. Now, when we rotated about the y-axis, let's see what direction we rotated. See if I can remember. I wanted to preserve this right-handedness of this right-handed sense. Again, you don't have to, but I had to make a choice on how to do that rotation. If we're going to rotate about the y-axis, let's see. I think, yeah, as I recall, I said take the x-axis and rotate it down this way. Because when I rotate it down this way, then my thumb would point out the y-axis, towards the y-axis, maintaining sort of a right-hand rule. Is that the direction that I want to rotate in? Yes, it actually is. That is the direction we want to rotate in. So beta will stand. We had to induce this negative sign over here. We don't here. Maybe I should write this down somewhere. So beta is going to be sine inverse of z sub naught. Alpha is going to be negative tangent inverse of y sub naught over x sub naught. Theta was the original rotation. We're assuming that we've normalized v. So there's kind of a lot of things to write down here. Again, if you look up these rotation matrices, you're going to see a lot of writing because you really have to say what you mean by all these things. So again, we have to normalize v, so to speak. If it's not a unit vector, we make it a vector, just divide by its own magnitude. So presto, you get a unit vector as a direction vector. You would be given that, right? And then you would be given this theta. And then given this theta, and given this, well, we calculated alpha and beta. We got to remember what they are. So first we do a rotation about the z-axis using the angle alpha. Then, well, actually, yeah, the angle alpha. And then we did, well, this angle is, well, now I put a negative sign in here. So, I mean, yeah, there it is right there. So, I mean, is that the same thing in that picture? Yeah, this is alpha in the picture, but we want to rotate through negative alpha. Okay, so we've got this. So we rotate about the z-axis using alpha. Then we rotate about the y-axis using beta. Then we rotate about the x-axis using theta. So maybe let me just write this down here for a second. So we rotate, all right, let me say we rotate about first the z-axis using beta. Then we rotate about the y-axis using alpha. We rotate about the x-axis using theta. And then what? We need to rotate about the y-axis using negative alpha. And then finally rotate about the z-axis using negative beta. I had mentioned this before, as of course the textbook mentions this. What would this be? This would be a composition of functions. Composition of functions. How do you accomplish a composition of functions? Where each of these functions is accomplished via matrix. So we do matrix multiplication. So what we would have is, first we would do this. Let me think of maybe a good way to write this. I probably won't come up with one, but a rotation about the z-axis. And let's put this in here. We're going to use the angle beta. So a rotation using that angle. And then we multiply on the left by a rotation about the y-axis using alpha. Then we rotate about the x-axis using theta. And I didn't give myself enough room here, but I don't think I need this anymore. And then we rotate about the y-axis using negative alpha, and then we rotate about the z-axis using negative beta. I don't know whether it's useful to put the dots in here or not. I don't think it's really adding anything. So this is a 3x3 matrix, 3x3 matrix, 3x3 matrix, blah, 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 blah. Every time you multiply 3x3, as we talked about, you get a 3x3. So here's what I'd like everyone to try to do. And me too, and I'll do it. I won't do it here on the video because it'll take some time. But let's say the direction vector, or I won't even give it a normalized vector. Let's say V is the vector 3, 4, 1. So there's our direction vector. I'll use the standard diamond brackets here for that. There's our direction vector. So you'll have to normalize that first before you get involved in all this. And let's say that theta is pi over 6 radians. Okay, I mean, remember, we don't write radians, it's soon to be radians, so I'll just flip it off. It looks a little neater. Okay, so given this, determine the matrix which will rotate R3 about the line determined by this direction vector, pi over 6 radians. What does that mean you're going to have to do? You're going to have to figure out alpha, beta, these 1, 2, 3, 4, 5 matrices, and then multiply them, and you will get one matrix. And that one matrix will do what we want it to do. So determine that matrix. And then let's see who gets it right. Hopefully I'll get it right too. What I mean, right, I mean, there's a lot of calculations to be done. Maybe, there'll be some things you have to do in terms of simplifying trigonometric things. Okay? I wish you all luck.